So in section 4, we're going to talk about graphs of rational functions. So we're going to combine everything we've talked about in sections 1, 2, and 3 in order to determine what the graph of a rational function is going to look like. And we can always use Desmos to help verify that our information is correct. So we're going to look at our first function, f of x equals 2x minus 6 over x plus 3. So every piece of information we find is going to help us with our graph. So the first thing we want to find is the domain. So remember, when we look at in order to find the domain, we find what makes the denominator 0 and exclude it. So my denominator is x plus 3, so I know that x cannot equal -3 in my domain. That also tells me what the vertical asymptote is. But first, let's go ahead and factor our numerator, make sure that the vertical asymptote isn't a whole. So if I factor in my numerator, I know that there's a GCF of 2 I can factor out. So I have x minus 3 left in parentheses all over x plus 3. So since no common factor cancels out, I do have a vertical asymptote at x equals -3, and there are none for wholes because there's no common factor that cancels out. So next we're going to move on to a horizontal or slant asymptote. So remember, slant is used along with oblique. They're interchangeable. They mean the exact same thing. So in order to identify if we have a horizontal or slant asymptote, we have to look at the degrees. So the degree of my numerator is going to be 1, and the degree of my denominator is also 1. So the degrees are the same. So if the degrees are the same, it's a horizontal asymptote. So it's going to be y equals, and then we divide the leading coefficient. So the leading coefficient of my numerator is 2. Leading coefficient of my denominator is 1. 2 divided by 1 is going to give me 2. So y equals 2 is my horizontal asymptote. So that kind of covers sections 1 through 3. So next we're going to talk about identifying the y-intercept and the x-intercept from the graph. And it kind of comes from remembering the definition of what a y and x-intercept are. So remember, a y-intercept is the value we get when x is 0. So we're going to go ahead and plug in 0 for x. So we get 2 times 0 minus 6 over 0 plus 3. So I end up with 0 minus 6 in the numerator, which is -6, and 0 plus 3 in the denominator, which is 3, which simplifies to -2. So I know I'm going to have a y-intercept at 0, -2. And if I notice, my y-intercept came from the ratio of the constants in my function, because for a y-intercept, when you plug in x or 0, all the x terms will disappear, will kind of cancel out, and you're just going to be left with the constants in order to divide. So that's how we're going to get our y-intercept. Our x-intercept is the value for x we get when y is 0. So this time we're going to set our equation equal to 0. We end up with 2x minus 6 over x plus 3. And now we're going to solve for x. My first step is going to be to multiply both sides by x plus 3. And when I do 0 times x plus 3, I'm left with 0. So I end up with 0 equals 2x minus 6. So now I'm just solving for when 2x minus 6 equals 0. So we go ahead and add 6 to both sides. We end up with 2x equals 6, divide by 2, and we get x equals 3. So that tells me we're going to have an x-intercept of 3 0. And if you notice, because when we set it equal to 0 and we multiply it by the denominator to start solving for x, we end up with the numerator. If you're solving for an x-intercept in a rational function, you find when the numerator equals 0. So there's kind of shortcuts you can take when you're identifying y-intercept and x-intercepts of rational functions. So now that we have all of this information, we can start putting together what our graph is going to look like. So let's start with drawing in our vertical asymptotes, horizontal asymptotes, and holes. So we don't have any holes. So let's go ahead and start with the vertical asymptote. There's a vertical asymptote going through -3, the x value. So I go to -3 on the x-axis. I'm going to draw a vertical line. And I have a horizontal asymptote at y equals 2. So along the y-axis, we're going to draw a horizontal line through 2. So that gives us our asymptotes, kind of breaking down what our graph is going to look like. So now let's go ahead and graph our intercepts. So we have a y-intercept at 0, -2. Go ahead and put a point here. And we have an x-intercept at at 3, 0. So that kind of helps me determine what the graph in the bottom right quadrant of my graph is going to look like. It's going to appear something along this line, along these lines. That's the kind of the general shape of the graph. And then I'm going to use Desmos to pretty much figure out what the other part of my graph is going to look like. And it appears in this top left space for the rest of the graph. And that's kind of what the graph of our function is going to look like. Okay. Let's move on to our second example. So we have h of x equals 25x over 2x squared minus 50. So we want to go ahead and in order to find our domain, we're going to want to go ahead and factor our denominator. So our numerator is going to stay 25x. I'm going to factor out the 2 first, and we end up with x squared minus 25. Which when factored, because it's a difference of squares, gives us 2 times x plus 5 times x minus 5. So for our domain, we know that x cannot equal -5 or 5, since that's what makes our denominator 0. And then if we look to identify vertical asymptotes and holes, there's no common factor that cancels out of my numerator and denominator. So x equals -5 and x equals 5 are our vertical asymptotes. And similar with our first example, we can put none for the holes. So next we move on to horizontal or slant asymptotes. So we look at the degrees, and if we look at our numerator, it has a degree of 1, and our denominator has a degree of 2. So this is an example where the numerator is greater than the denominator. It is a horizontal asymptote, and it is of the form y equals 0. Let's go ahead and move on to our y-intercept. So remember, y-intercept is what we get when we plug in 0 for x. So we take the ratio of our constants. So there is no constant in our numerator, so it's 0 divided by -50. So our y-intercept is going to be at 0, 0. And for our x-intercept, because it would be solving for when our numerator is 0, 25x equals 0 when x is 0. So our x-intercept is also 0, 0. So let's go ahead and start graphing our function. So we have our horizontal asymptotes through -5 and 5. And we have a horizontal asymptote of y equals 0. So when we go to graph our function, because we know that our x and y intercept is the point 0, 0, go ahead and put a point there. We notice it kind of contradicts the fact that we have a horizontal asymptote through the origin. The reason this happens is that if we graph our function, it actually has 3 parts to it. It has a part in this bottom left part, and it also has a graph in the top right. And then it actually has a graph in the middle. And anytime we have a graph between two vertical asymptotes, I should say, it can go through a horizontal asymptote. So this is actually a special case of a vertical function. Rational function. It still has horizontal and vertical asymptotes like we identified, but then it has this middle function that will go through the origin, which is allowed. It can pass through the horizontal asymptote in this case. Let's go ahead and take a look at our last example. So our last example is the function g of x equals 2x squared minus 5x minus 12 all over 2x minus 1. So when we go to identify our domain, the denominator is already in factored form, so x cannot equal, and then 2x minus 1 is 0 when x is 1/2. So x cannot equal 1/2. Now in order to identify if we have vertical asymptotes or holes, we need to go ahead and factor that numerator. So I'm going to do that off to the side here. 2 times -12 is -24, -5. So we're looking for numbers that multiply to -24 but add to -5. And that is going to be -8 and 3. Divide both of them by 2. -8 over 2 simplifies to -4. So our numerator is going to factor to x minus 4 times 2x plus 3. All over our denominator of 2x minus 1. So there is no common factor that's going to cancel in our numerator and denominator. So our vertical asymptote is going to be at x equals 1/2. And we don't have any holes again. Just because none of the examples in this section of notes don't have any holes doesn't mean that you're not going to run into examples that you have to solve that do contain holes. So next we're going to move on to the horizontal or slant asymptote. So if we look at the degrees, the degree of our numerator is 2 and the degree of our denominator is 1. So this is a case where the degree of the numerator is greater than the denominator, which means we are going to have a slant or oblique asymptote, which means we're going to have to use long division to find our asymptote. So 2x minus 1 on the outside, 2x squared minus 5x minus 12 underneath. So we start out with 2x squared divided by 2x, which is going to give us x. We go ahead and multiply x times 2x minus 1. We get 2x squared minus x. Remember, we put it in parentheses because we are subtracting. 2x squared minus 2x squared cancels. Negative 5x minus a negative x turns into addition, and negative 5x plus x is negative 4x. And then we're going to bring down the negative 12. So now we're going to do negative 4x divided by 2, which is going to give us negative 2. So now we multiply negative 2 times what we're dividing by. We end up with negative 4x. And then negative 2 times negative 1 is positive 2. Put it in parentheses, we're subtracting. Negative 4x minus a negative 4x cancels. Negative 12 minus 2 is negative 14. But remember, we don't care about the remainder when we do the long division. We only care about what we end up with as our quotient at the top. So our slant asymptote is going to be the equation y equals x minus 2. So now we're going to move on to our y-intercept, which is going to be dividing our constants. So it's going to be negative 12 divided by negative 1, which is going to be at 0, 12. And then our x-intercept is going to, well, in this case, it's going to be 2 x-intercepts. It's when our numerator is 0. If we look, our numerator factored is x minus 4 and 2x plus 3. So we're going to have 2 x-intercepts. One is going to be at 4, 0. And our second is going to be at negative 3/2, 0. So now we can go ahead and graph our rational function. So we're going to start with our vertical asymptote going through 1/2, which is going to be a little bit difficult to see since our graph goes up by ones. It's going to be somewhere along here. And then our slant asymptote in this case is the equation y equals x minus 2. So we are going to graph that line. So y-intercept negative 2, apply a slope of positive 1. Something along these lines. And this is a rough estimate of the line y equals x minus 2. So now we can go ahead and graph our function. And if we use Desmos as kind of like a guide, it's going to be an interesting shape because of that that slant asymptote. It's going to take along an interesting shape. So it's not going to look exactly like a rational function that we know, but it is still a rational function.